Hi, everybody. So the last little section here in our review notes talks about graphing and slope, and we will talk more about slope with slope-intercept form, y equals mx plus b, during the actual Module A notes. But I just wanted to give you a quick overview reminder of graphing. So at the beginning here of these notes, just a little bit of review. This is the x-axis, this is the y-axis. Technically, these axes do have arrows on the ends. You'll see most of the grids I have don't, just because of the way I did it. It's a little easier that way. But technically they do have these arrows that I drew in here. We talk about quadrants. So quad, think about four. The quadrants are when we use the axes to split the coordinate grid into four equal parts. So we number them with Roman numerals, 1, 2, 3, and 4. I always think of it like if I start here and make a C, that's the order that they go in. And then we need to know this is the origin right here where the two axes cross. I just have some examples of graphing some points there as review. This should all be review. If it's not, please let me know so we can go over it a little more. And then when we're trying to graph a linear equation, then, for example, we have y equals x minus 3 or x minus 3 equals y. We can choose any values of x that we want. I just chose some here. Then we're going to find out the y value for each of those by plugging in that value of x. So if x is negative 2, I put negative 2 here. Negative 2 minus 3 is negative 5. So my point, my xy that goes together is negative 2, negative 5. I graphed that here. I did the same thing for these other points. So my points are here. Here is 0, negative 3. Here is 1, negative 2. Here's 4, 1. And then I connect them using a ruler or some kind of straight edge. And I label it with my line. So this line is made up of an infinite number of points, right? Not only the points that go through the actual grid intersections here, where the values are whole numbers, but even in between, like this point right here would be 1 point something, comma negative 1 point something, right? The little decimals in here. So every single point on this line would make this equation true. So if we're asked if this point is on this certain graph, this is a different line, then we substitute in the x and the y. And if those two things make this equation true, it is on the line. If they do not, then it's not on the line. Slope. So slope of a line is how steep that line is. Here's our slope formula, y2 minus y1 over x2 minus x1. Notice it's not y squared and x squared, okay? It's just little labels to show I have 1 point, I'm going to call it x1, y1. I have another point, I'm going to call it x2, y2. It doesn't matter which point I call what, and I'm going to subtract those. All right, so when we're talking about slope also, a positive slope goes in this direction. This means that as x goes up, y also goes up. A negative slope is going to go in this direction. So as x goes up, y came down. One easy trick I have to remember this is if a line is in the direction of a negative slope, and it could be more shallow or more steep, but in this direction, you can make an N out of it. It's tipped the same way as the slanted part of a capital N. A horizontal line has 0 slope. Again, little trick, you can make a Z out of that. And a vertical line has what we call an undefined slope. Because if you think about the slope formula, it's the change in y over the change in x. Well, this one, between 2 points, there is no change in x. So it'd be 0, and we can't divide by 0. We can also think, you might remember rise over run. So to get from one point to another with slope, we rise a certain distance. It's either up or down, like an elevator. We run a certain distance, left or right. Okay, so that's kind of just a visual description of what's happening to go along with the mathematical description of what's happening up here. So here are a couple examples. For this one, find the slope of a line that goes through these 2 points. So I'm just going to call one of these 0.1 and one of them 0.2. I didn't even put in the little subscripts here. But I'm going to show you here that it really doesn't matter which you call 1 or 2. So I have to subtract the y's. Remember, even though the y is after the x, here, The y goes on top here. It's a little bit confusing there. So 9 minus 3. Then I have to subtract the x's in the same order. 4 minus 1. 6 over 3. I can reduce that to 2, or 2 over 1. So if my slope is 2 over 1, again, think about rise over run, or change in y over change in x. This means that if I'm at a certain point on my line, whatever my line looks like, to get to the next point, I'm going to go up 2 and to the right 1. So it kind of needs to be a little steeper, huh? But I'd go up 2 and over 1 to the right. Rise 2, run 1 to get to the next point. Now I just wanted to show you where it says or here, I subtracted the opposite way. So I said, okay, I'm going to do 3 minus 9. Still the y's, but the other direction. 3 minus 9. If I do that, I have to do the x's in the other direction. 1 minus 4. I get negative 6 over negative 3. That still reduces down to a positive 2. So it does not matter which order you subtract in. The two important things to remember are your y's go on top, your x's go on the bottom, and whatever order you subtract your y's, you have to subtract your x's in the same order. So again, finding slope from here, finding slope from the graph. I kind of explained there how to do that. And then here we're just graphing given a slope and a point. So kind of what I just talked about here. If I know a starting point, for example, here, I know that my starting point is going to be 1, 1, which is this point right here. If my slope is 2 over 3, then to get to the next point on the line, I know I need to go up 2 because rise and it's positive. Right 3 because it's positive. There's another point. And then I can do it again, up 2, right 3. I can also reverse both and go down to left 3, and you see that's on the same line. And we'll use this when we get into, in Module A, when you're doing the graphing based on the slope-intercept form, we'll use that. And then finally here, solving for a variable. So if I have a linear equation that has more than one variable in it, okay, the ones we did before only had an x. Here this has an a, a b, and a c. So if I have this equation, then I want to solve for one of those variables. That means I want to get a by itself, just like before we would have x equals something. Now, because there's more than one variable, these are not all like terms, so they won't combine. So we'll have more than one thing on that right side. It won't just be a equals 8. It'll be a equals stuff with b and c in it. So you can see we're going to use the same process, though. I always talk about using the same process, even though it looks different. If I want to get a by itself, I'm going to move this thing away that is still on the same side as a. If I have positive b, I get rid of it by subtracting b. Then I had 3a equals 2c minus b. I want to get rid of the 3, so I divide every single term by 3. We're going to get in the habit of writing the 3 under each term separately. You'll see in this next example when you try it, that allows you to simplify some things, and also that's what we need to do in the next section when we're graphing. All right, so that's kind of my quick overview, end of the review for Module A. If any of those things were completely new and you just can't quite grasp them based on the notes, then please let me know, because we do need all these things in Module A for this week. All right, thanks guys.